So welcome to Operating Systems Lecture 8. Right. So far we have been looking at how an operating system implements the abstractions that it does. And the first abstraction we looked at was the address space. And we said, look, segmentation is one way to implement address spaces. And there's a structure called a global descriptor table, which lives in the physical memory. It is roughly of the size 2 to the power 13. Which is perhaps the reason why it should live in the physical memory, right? Because the chip will not have that much capacity to be able to store large structures like this. So structures like this, which are relatively large, need to be stored somewhere else, and the typical place they're stored in is memory, right? And then, but on the processor, you have this register, which is called the global descriptor table register, which points to this GDT, and that's how the hardware knows where to look for when it's actually executing the MMU operations, right? Now these registers, code segment, data segment, etc., these are called the segment registers, and within them they store the segment selectors, right? Depending on the instruction, a virtual address will choose one of these registers. For example, if you are dereferencing the instruction pointer, you will go through the CS register. If you are dereferencing any regular data, the default segment will be the data segment, so you will dereference the DS register. If you are dereferencing the stack through ESP or EBP registers, then the default segment will be SS register. So there are certain default segments, and then you can also override the default segments by explicitly specifying that this is the segment register that I want to use for this particular address. In any case, the segment selector is used to index into the GDT. So the algorithm inside the hardware is that it will first dereference GDTR. It will first read GDTR to find the address of GDT, add the selector to that value to understand where exactly the descriptor lives, read the descriptor, get the corresponding base and limit values, perform the appropriate operation of PA is equal to VA plus base and checking if VA is less than limit, and if these checks succeed, it actually uses the computed physical address to index the physical memory. All right, question?
So is the value of GDTR checked at every memory access instruction?
Is the value of GDTR read at every memory access instruction? That's a great question. In other words, for every memory access, do I make another memory access? So does every memory access that a program makes, does the hardware need to make two memory access, one to the GDT and then one to the real physical address? Well, logically speaking, yes. But actually no, because these entries get cached inside the chip, right? So there are semantics on when the caching takes place and when it gets invalidated, and let's ignore that discussion for now. But you can imagine that the descriptors for all the 6 segments that are present on the CPU, they just get cached inside the CPU. So you don't have to go over the bus every time to access the GDT descriptor, right? So that's an optimization, but let's look at the semantics for now. So each segment descriptor has a base and limit, and it also has permissions, which basically says at which privilege level am I allowed to go through this segment, all right? So the privilege level is determined by the lowest 2 bits of the CS register. So if the lowest 2 bits of the CS register are 0, which means I am executing in privileged mode, I can access any of the configured segment descriptors here. Or I can dereference through any of the segment descriptors. On the other hand, if it's 3, then I can only dereference segment descriptors that have permission set to 3, right, or unprivileged. All right. So far so good. Basically, what this allows you to do is every process will have a private address space. Nobody else can touch it. The OS will have its own protected address space. No process can touch it. And moreover, each process has a uniform address space. Starting at 0, for example, right? So the compiler or the linker does not need to be worried about where the process will actually get loaded. So the loader and the linker can become completely independent in some sense. All right. The next thing we said was, look, that's fine. This is how operating system implements address spaces for processes, but a process needs to do more. In particular, there needs to be a way for a process to make a system call. There needs to be a way for the OS to actually take control away from the process on some external event, like an interrupt from an external device, or an interrupt from a timer device, for example, especially because I need to implement protection. So one process should not be able to run away with the CPU. So I should be able to run after every predefined time interval. Moreover, I should be able to get control if the process performs any illegal action, like divide by zero, segmentation violation. So the word segmentation fault actually has historical roots in the segmentation procedure. So a segmentation fault means that you violated the segmentation rules, right? So you actually tried to exceed the limit, and so you violated the segmentation rules, and that's how that's why it's probably called segmentation fault. All right. So to facilitate this and also system calls, there is a mechanism called the interrupt descriptor table, or IDT as I'm going to call it. And the idea is that in case of an event which is either an external event that a device needs attention, it asserts the interrupt pin, or it's an internal event that the application actually executed something illegal or the exceptional condition, then the processor is going to stop execution there for the process and look into the IDT to figure out where is the handler of this particular condition, right? The condition could be an external device asserting something, or the condition could be internal. In either case, there will be a number associated with that particular condition, and that number is called the interrupt vector. So the interrupt vector will determine which entry in this IDT should be dereferenced, and that entry is going to be used to find the program counter of the handler, right? So each descriptor in the interrupt descriptor table contains a pair, code segment and EIP, which is basically a pointer to the handler of that particular condition, right? So for example, if the network device asserted the interrupt pin and you have assigned it number 2, then you should have the network device handler at this particular address. Or if there was a segmentation violation, then you should have the segmentation fault handler at this location and all. And these handlers will typically do what? They will either execute the device driver logic in case it's an external interrupt, or if it's an exceptional condition, they will execute the appropriate logic to deal with that exceptional condition. So for example, if it was a segmentation fault, the operating system could say, let's just kill the process, all right? Or it could convert that exception into a signal and pass it on as a signal to the Unix process, right? And recall what a signal is. A signal is nothing but interrupting the process execution and making a call to the signal handler of the process, right? So in some sense, the abstraction of Unix signals is very much inspired from what happens at the hardware level in terms of exceptions and interrupts, right? So an interrupt also causes a handler to get executed, and the signal got, but in this case it's the interrupt handler. In case of a process, it was a signal handler, which was the process had registered. The process was able to register signal handlers for itself. Similarly, the operating system should be able to register interrupt handlers or exception handlers for itself. The mechanism to be able to register signal handlers is provided by the OS. The mechanism to register interrupt handlers or exception handlers is provided by the hardware, right? Okay. All right. So we understand handlers so far. The other important thing is that the code segment could actually be a privileged code segment. So even if I am executing in unprivileged mode, if this code segment has last 2 bits set to privilege, which is 0, then when the interrupt is going to occur, it's going to start executing in privileged mode. And that's required because you want that whatever code you're going to have for device drivers or for exceptional conditional handling should run in privileged mode, right? So the hardware designers provide that facility by allowing you to specify any CS here. All right. Okay. All right. So with that, let's look at what happens if so before I start, an interrupt or an exception. So I use the word interrupt for anything that's from an external source, like external device, like a timer or a disk or whatever. And I use the term exceptions for something internal, like a segmentation fault or a divide by zero, etc., or an illegal instruction was executed, etc. Right? So an illegal instruction is executed. One example would be a process tried to execute a privilege instruction, like LGDT, right? So we saw that loading the GDTR is a privileged instruction. If you are running in unprivileged mode and the process tries to execute the privileged instruction, LGDT, right? You recall the LGDT instruction, which loads the GDTR. The process is not going to be allowed to do that, and what will happen is an exception will get raised and the operating system will come into action and it will decide what to do with the process, right? All right. And another thing, the IDT itself is also stored in memory. Once again, IDT is a relatively large structure, cannot be stored on chip completely. So rather the IDT is stored in memory, and there is a pointer called IDTR inside the chip, which basically says where to look for IDT, just like GDT. All right. So now let's say I get a trap. So I'm going to use the word trap as a general term for interrupts or exceptions. So I could get an interrupt, I could get an exception. Let's just call them a trap. This is the question. Can we change the entry in the IDT? Let's hold that thought for a moment. That's a great question. But let's just first understand how this works, and then we'll talk about security. What should a process be able to do and what it should not be able to do, such that it's not able to gain control of the system. So let's say I get a trap in kernel mode. Kernel, or you can also say privileged mode. Right? So I'm going to use privileged, unprivileged, or kernel user, same thing. Right? So kernel is privileged mode, kernel mode is privileged mode, and user mode is unprivileged mode. So what happens is, let's say I was executing and a trap occurred. So what will happen is, let's say this was my stack pointer, this was the value of my stack pointer. As soon as a trap occurs, what I'm going to do is I'm going to push the old values of CS and old value of EIP, and I'm going to set my CS and EIP registers to the values which I get from the interrupt descriptor table, and I'm going to now start executing, right? So I got the trap in the kernel mode. I used the ESP value at that time to push the old values on the stack, and now I start executing the interrupt handler, right? This is very similar to how signal handling was happening, right? A signal comes, you just execute it as a function call, as an asynchronous function call. Similarly, this is doing a similar thing. An interrupt came or a trap happened, you just executed the handler as an asynchronous function call, using the same stack that the kernel was using, right? Okay. Another matter of detail, apart from CS and EIP, it also stores old E flags, right? So the interrupt descriptor table entry could also potentially contain flags register or certain flags, and when the interrupt gets actually starts to run, the semantics are that you're going to replace not just CS and EIP, you're also going to replace certain flags, some flags, right? So before you start execution of the interrupt handler at this point, you're also going to replace some flags with the values that are present in the descriptor, and because you're going to change things, you also need to save them, and once again you save them on the stack, right? So this is clear?
So this is stored in the kernel stack.
This is, yeah, so we are talking about a trap received in kernel mode. So let's say there's an interrupt while I was executing in privileged mode. This is what will happen. So it'll just push things on whatever the value of ESP is currently. Okay? Don't we require storing general purpose registers? Yes, we do require saving more things, but this is the minimum that the hardware saves for you, and now the control has been transferred to the handler, and most likely the first thing the handler is going to do is save the rest of the state. It may
Handler is a part of OS only.
the handler is, yes, part of the OS.
But this transfer takes place via hardware.
Via hardware, yes. See, basically the hardware has to change the values of some registers to be able to execute the transfer, and so whichever registers it changes, whichever is the minimum set of registers it needs to change, those are the set of registers it saves. Other things it doesn't need to change. It's really up to the software writer whether he needs to save them or not, right? These kind of things the software writer won't have been able to save, right? Because you have to say where to execute the handler. And so before the, I mean, it's a chicken and egg problem, so the hardware has to come into the middle and says, okay, these are the things I will save, and the rest of things you can save. Right, so there are certain flags I'm going to see later, which need to be saved by hardware. So why can't E flags be also saved in software, right? So there's a reason for that, and we're going to discuss that later on. Let's just live with it for now. All right, so this is what happens on a trap entry, right? And then the handler is going to execute. Typically the handler is going to execute on the same stack, so it's not going to change the stack value, right? So it's just like an asynchronous function call. You just execute the handler, and then you want to return from the handler, right? In case of a signal, when we saw for Unix, I just executed the return instruction, and I will get back to where I was, right? Because the semantics of the signal entry was that the OS used to push the return address on the stack. And so when the signal handler used to call return, I used to pop the return address on the stack and get back to where I was, right? In this case, also it's going to be similar, except that it's not a regular function call, so I cannot just use return to return, because return is only, the semantics of the return instruction is that I just pop the stack and look at the EIP, and that's it, right? I just pop the EIP and set that. It has nothing to do with CS and E flags. Yeah, recall the return instruction. So we need a special instruction called interrupt return, IRET. In trap return, I'm going to call it trap return. All right. And here, if the ESP is pointing at this place, an interrupt return is going to pop the stack and put the first value into EIP register, the second value into CS register, and the third value into E flags register, right? So this is the semantics of the IRET instruction. What it's going to do is, it's going to look at the current stack pointer and pop the first 3 words on the stack and fill these registers with those values. All right, so this is return from interrupt. Yes. Yes, so right now I am talking about a trap in the kernel mode, right? So because I was executing in the kernel mode already, so ESP is of the kernel, all right? So I'm already executing in the kernel mode, so ESP is trusted in this case. So I can do these things. Now next I'm going to talk about traps in the user mode. That was the discussion that we were having yesterday, right? As a matter of additional detail, there are some vectors, there's some interrupt vectors which actually push 4 words, right? This is just a matter of the fact, really. There's no fundamental behind it, but there are certain vectors for which there are certain extra there's one extra value that's pushed, that's the error code. All right. So for example, the page fault. For example, you can say a certain exceptional condition could additionally push this error code for the handler to know exactly why that exception occurred. Right. So certain exceptions can occur because of various reasons, and so an extra value is pushed onto the stack to indicate that. Right. So only the hardware knows exactly why this exception occurred. So one exception could actually be representing multiple conditions, and so error code basically tells you which of these conditions is actually the reason for that exception. What this means is, because some vectors push the error code and others don't, the handlers need to be appropriately set up such that they understand this, right? So the handler for the vectors which push the error code will be set up to know that an error code is already there, and the handlers for which the vectors which do not push the error code should know that it's not there. Just to simplify things, typically on x86 an OS handler will, all the handlers for which the error code is not pushed, the handler will, the first thing it will do is just push a 0 value there, so that the stack becomes uniform, right? So it can assume a uniform stack frame, really, right? So if there was no error code pushed by that vector, the OS in software will just push a 0 for that particular handler. So on return, the IRET instruction does not assume the presence of error code, all right, irrespective of what happened here. Right? So it's the responsibility of software to pop the error code before it calls IRET. Okay. All right. Okay, now let's look at a trap in user mode, right? Or let's say unprivileged mode. Okay, once again I was executing, and here's my stack pointer, that's where it's pointing, and a trap occurred. Now what should the kernel do? Can it do the same thing? Can it just push? So clearly it needs to override certain registers. For example, it needs to override CS and EIP, definitely. It also needs to override E flags. Okay. So now question is, where does it push the old values of these registers? Because it needs them at interrupt return. So where does it push them? It wants to push them on stack, but can it just push them on this stack? Why? Because this particular value of this register is modifiable by the user, and the user could set it to anything which cannot be trusted. Right? I don't trust. So the model is that I don't trust the process. I don't trust the process in the sense that I won't let the process bring down the whole system. No matter what the process does, it should never be allowed to bring down the whole system. In this case, if the process had just set ESP to 0, for example, right, or some invalid address, and then right, so let's say ESP was set to 0, and then it executed some exceptional condition which caused a trap. Then what will happen is the kernel will try to push on a full stack, right? 0 cannot be decremented any further, and so it will get into an infinite exceptional condition, and the CPU will actually halt, right? So that's not acceptable. So what's really needed is that if you receive a trap in user mode, you should also switch the stack pointer before you start pushing things, right? So what happens is, on a trap, it actually switches to another stack, and that stack is, let's say, ESP 0, and then on that stack it's going to start pushing things, right? Notice that because I'm modifying more registers now, unlike the previous case where I was just modifying CS and EIP, I'm now also modifying ESP. In fact, I'm also modifying SS, right? So the semantics are that I'm going to modify the entire virtual address which is represented by SS:ESP. So initially if it was SS:ESP, now it becomes SS0:ESP0, and so I need to save the old values of SS and ESP, and I'm going to do that on this stack, right? So what I'm going to do is, I'm going to push 5 bytes here, and I'm going to say, let's say, old SS, old ESP, old E flags, old CS, and old EIP. Right? So these are the things that the hardware saves for you, and now the interrupt handler is set up to be able to run in a secure environment. So it has a secure stack that I didn't trust, and it is on the right instruction pointer, and now it can start running, and it may want to save more things. And typically it will also save those things on the same stack on which it was started, right? Because this is trusted stack anyways. Okay?
The second one is the kernel stack.
The second one is the kernel stack. This was a user stack. Right? Now what happens if when the kernel executes the irate instruction? So now the interrupt handler will execute, or the trap handler will execute on the kernel stack, and eventually it will want to return, and it should actually return to exactly the same point in the user space where it actually left off, right? So once again it's going to call the irate instruction, and the semantics of the irate instruction is going to, once again, let's say this was the ESP at this point, it's going to pop off the first 3 words and set those up as CS, EIP and E flags, just like before. But now it's going to see that, oh, the CS is actually an unprivileged CS, right? So the CS that it's actually popping into the into the register is actually an unprivileged CS. It can see that from its value, and so it's going to realize that because I transition from a privileged to an unprivileged, I'm transitioning back from a privileged to an unprivileged mode, there must have been 2 more words that must have been pushed, and so it also pops off those 2 words and actually pops off 5 words to basically reload these registers back again. Right? So in the previous case, irate was just popping 3 values. In this case, irate is popping 5 values. How does irate know how many values to pop? By looking at the value that was popped in the first 3 words, right? Or by looking at the value of the second word, right? That contains the CS. All right. And so when you execute the irate instruction, you are actually going to get back to the user stack, right? Because you have changed the value of SS and ESP, so you are actually now going to start executing in the user stack with at exactly the same EIP at which you left off. Okay, so now let's talk about security. So what prevents a user from being able to take control of the system? So we said a user is basically sandboxed within his own address space because firstly he cannot modify GDTR. Secondly, we said the GDT itself should live in a portion of memory that's not accessible by the user, right? And thirdly, the values of these selectors can only be set to one of the values that have been put in the GDT, right? And the OS should be careful that it only puts the right values or permissible values in the GDT, right? So that's how I was ensuring that a user is not able to jump out of its address space. Question.
Previous one, how do we ensure that in the kernel mode that ESP never becomes 0?
Okay, good question. So how do we ensure that in the kernel mode, ESP never becomes 0 or ESP never underflows, right? Or I never run out of stack. So this is something that an OS designer has to be careful about. Nothing in this world is infinite, right? Infinite. So even in the user mode, a stack is never infinite. It's just an illusion of infinity, right? So if you ever try to cross your boundaries, you are going to if a process ever crosses its boundaries, it's going to get a segmentation fault. Okay, and OS should ideally never cross its boundaries. So the OS designer should write his OS in such a way that there's a bound to the maximum stack length that you can have. All right, I'm going to see how that's done. So an OS designer or an OS writer or kernel developer has an extra bound that you cannot grow the stack too much. There's a maximum bound to how much a stack can be. Typically, a stack would be, for example, the Linux kernel has a stack of of around 4,000 bytes, or maybe even 8,000 bytes, right? So between 4,000 to 8,000 bytes are enough in general for a stack, right? Even your XV6 kernel, which we're going to look at an academic kernel called XV6 later, it also has 4096 bytes of stack, and that's enough for most purposes. Okay. All right. Okay. So we saw how this is basically saying that a program can never jump out of its address space. It's also saying that a program can never execute an instruction which is privileged, because I'm going to run it in the privileged mode, etc. Okay. And a program can never lower its privilege level. So once you have set up the privilege of the CS register, I cannot just lower the privilege level. But we also saw that the IDT is a way for the process to actually lower its privilege level, right? So for example, I can just execute some exceptional condition, and I'll now be executing in privileged mode. So the first thing is that the OS should ensure that all these entries, all the handlers of the IDT are pointing, all the entries in the IDT are pointing to valid values. If one of these IDT values is pointing to some garbage, then an OS can actually cause that particular vector to get fired, and you are going to actually try to execute some invalid instruction, and the system can get down, right? The first thing is the IDT itself should have completely sane values. The second thing is the instruction to load the IDT, which is the LIDT instruction, which just loads the IDTR, should be a privileged instruction, right? A user shouldn't be able to just say LIDT, right? Because if the user can say LIDT, then he can just take control of what gets executed in privileged mode. So the instruction LIDT should be a privileged instruction. All right. The third thing is that the IDT itself should live in the OS address space. It should not be visible to any process. Okay. So only the OS can set up these values. The OS needs to be very careful about setting up these values, so the user cannot take advantage of any bugs in the OS. Plus, you basically ensure that this structure is not modifiable by the process. Okay. All right. Okay. Yes, question. Okay. Is it possible that a process wants to handle an interrupt in a different way than another process? It is a matter of what abstractions the OS is providing to the process. In the abstractions that we've seen so far, that's not possible. A process has no idea what an interrupt means, right? It only understands system calls and signals. Okay? So it doesn't make sense to say that one process should be able to control the handler of a particular interrupt, right? A process can control the handling of a particular signal, right? So that's a difference. Of course, so what you put is you put a layer in between the hardware and the process, and you have said that these are the permitted things that you can do, and I'm going to implement those things, right? And we have seen one type of abstractions, that are the Unix abstractions, and then there are other types of abstractions which actually allow the kind of thing that you are saying, all right? And there are performance advantages to be able to do that, right? But it also makes things more complex and etc. And we are going to look at those trade-offs later on. Okay. All right. So in this figure, when I said that when a trap is received in user mode, I actually switch the stack to SS0 and ESP0. There is a minor matter of detail. Where does the hardware get these values, SS0 and ESP0, from? Right. So there needs to be some way of telling the processor that, look, these are the values of SS0 and ESP0. Before the OS actually gives control to the user, he should set up SS0 and ESP0 appropriately, so that if a trap occurs while the process was executing, the hardware knows that this is what you should load, right? And on x86, there is a structure called task state segment, which allows you to do this. And there are more details that you're going to find out in your programming assignment. I'm not going to go into detail. Let's just, for the purposes of our discussion, let's just assume that there is some place where you can store these values and tell the hardware that here's where you should pick up these values from, right? When you get an interrupt in user mode. Okay. Another thing I would point out is that notice that when I'm talking about the semantics of instructions like iret, while the semantics have been designed in such a way that they complement or they bracket the operation at interrupt entry, or they, so whatever the interrupt entry is doing, iret is undoing. But actually, iret exists as a separate instruction in itself, right? Which has these semantics that's going to pop off the first 3 words and load them into these registers, and depending on its values, maybe pop off 2 more words, etc. So actually, between the execution of the entry, between the entry and the return, the interrupt handler could potentially modify these values, right? For whatever reason. Typically, it will not modify these values, but sometimes it may, right? One example where it may modify these values is, for example, when you want to set up the first process, or let's say when you implement the fork system call, right? So what happens in a fork system call? Okay, before we discuss that, let's also talk about how system calls are implemented. We discussed that yesterday, but let's review that. So apart from interrupts and exceptions, there are also something called software interrupts. These are interrupts that the program can actually invoke. So instead of some exceptional condition happening or some external device saying that I want an interrupt to get handler to get executed, the program itself could execute an instruction like int3, it's a 1-byte instruction, or int o, which basically says invoke this particular interrupt or trap. The semantics is that this is going to simulate an interrupt of vector 3, right? This is going to simulate an interrupt of vector whatever O stands for, overflow in this case, right? The semantics for this is that this is basically used for debugging. So this is the breakpoint, right? So if you have wondered how GDB works, for example, one it basically, so if you put a breakpoint at some point, you say I want to stop the execution at this particular point, right, at this particular value of the instruction pointer. What GDB does, one way to do that is basically that GDB writes this particular instruction int 3 on that particular byte. So let's say I wanted to get interrupted at EIP 1000. So what GDB is going to do is it's going to write int 3 instruction at 1000. It's going to replace the original contents of that value, EIP of that memory location and put int 3 there. What will happen is when the program gets executed, as soon as it reaches that point, it's going to execute int 3 and an interrupt is going to get simulated. The interrupt handler will be the OS interrupt handler, and in this case the interrupt handler will know that this is a breakpoint interrupt handler. The breakpoint interrupt handler, let's say what it does is it converts the exception into a signal that it gives to the GDB process, and so the GDB has installed a signal handler which basically says okay, stop execution and return back to the user with a prompt and ask for the next command from the user, right? So this is one way of implementing breakpoints, right? So a good example of why software interrupts are used, okay? Similarly, interrupt overflow is an overflow condition. So this basically says that if in the eFlags register the overflow bit is set, then cause an interrupt. So the way the hardware designers imagined this to be used is basically you perform some computation and then you execute the into instruction. So if the execution actually created an overflow, it will cause an interrupt. If it didn't cause an overflow, it will not cause an interrupt. And so the idea is in the common case when there was no overflow, you will just very quickly go to the next instruction. You don't have to have if then else kind of logic in your code. So this gives you a very nice, a fast way of doing this kind of exceptional condition handling, right? And of course then there is the normal int instruction which can take any vector number, and this can basically say simulate this particular interrupt, right? And this is what we use for system calls, right? So example, a particular vector number, let's say the Linux kernel had been using the number 128 or hexadecimal 80 to do the system call. So basically means if a process makes int $0x80, it's going to simulate an interrupt at vector 0x80, and the handler at 0x80 is going to assume that a system call was made. It's going to also assume that the arguments of the system call and the system call name itself is stored in certain places. For example, it's stored in the registers, and so it's going to read the values of the registers to figure out what system call I need to execute. For example, exec, fork, etc., and what were the arguments to it, right? For example, the address of the string for exec, etc. Okay. So system calls are also implemented by using this interrupt descriptor table structure, and okay, and so we were discussing how IRET can be used. So we said that IRET has just these semantics, and a handler may want to actually change these values before the interrupt runs. And one example where you would do that is the fork system call, right? What happens on a fork system call? You make a system call, the handler is a system call handler, it figures out that you are trying to call fork. What it does is it creates a new address space and copies your address space into the new address space. One way to create a new address space is get the same amount of memory in physical memory, right? Copy all the contents, set up a new base and limit in your internal data structures, and set up the stack in this way such that EIP, CS, eFlags, ESP, SS is identical to how it was in the process which called the fork, with the only difference being that the return value should be different, right? So how does it do that? Where is the return value stored? Yeah, let's say it's the the return value of the system call is in the EX register, so it just changes the value of the EX register and executes the irate instruction. So it sets up a new stack, it copies these values, it maybe changes some register and causes irate, right? Another way, a fork system call could potentially return is basically, store the value on stack, right? So let's say the return value is coming on stack, even that's possible. What the handler will need to do in the new process is dereference the stack pointer of the user and maybe change some values there before calling irate, right? And so the stack will actually see new values, slightly different values, let's say. Okay. Similarly, when the kernel boots, there's really no process. There's really no user mode. Everything is running in privileged mode. So when you create the first process, for example, the init process on Linux, what the kernel will do is it will just set up the stack in a certain way. It will set up the address space in a certain way, such that a certain executable will be loaded in the address space. And now we'll just call the irate instruction. And so now the first instruction of init starts executing. So even though init actually never existed before the irate, irate is basically simulating as though I'm returning back from a system call that it made, right? So basically a kernel can set up a fresh stack and still call irate, or it can modify these values and still call irate to implement desired functionality.
Sir, but while booting, can't it just move the values into CS and ERP through move instructions instead of first putting them on stack and then calling irate?
Okay, can't it just move? So you cannot just move into CS, right? There's no instruction which says move into CS. There's no instruction which says move into EIP. There are instructions like ljump, right? So that's an interesting question. Can you just say ljump to this particular value? And let's see, why is that not allowed? So you also need to change the stack. So you will basically need to load the stack from the user mode to the kernel mode, and then you're going to call ljump. I believe it's not allowed in the processor, so you cannot just say ljump from one privilege level to another privilege level, right? But let me confirm that. So exactly why the x86 architecture doesn't allow you to just do ljump. But more importantly, even this is an atomic operation, right? So you can just basically set up the stack and the EIP in one go, as opposed to doing it in multiple instructions. So first you will have to load the stack, and after you have loaded the stack, you're still executing in privileged mode. And so that also has its own security implications. Executing on an unprivileged stack in privileged mode has its own problems.
So we need to return to both the processes, the parent and the child.
Right.
How do we do that?
How do we do that? That's easy, right? The parent can just return. So for the parent, it was just a system call, a regular system call, right? So just like it returns from a regular system call, it's going to call irate and it's going to return from it. For the child, you need to create a fresh stack, right? So here's a process. It made a system call, right? The system call basically internally figured out it's a fork, and so it created new state, it created a new stack, it added a new process to its list of processes, and now it just calls irate on the original stack, right? So the parent can just continue as it is, right? And now the child, on the other hand, will continue on its new stack. We call irate on both, right? So only one process enters the kernel, and two processes exit the kernel. And the stack. So we are copying the entire address space, and we are setting up the stack pointer to be identical. So that basically means you're copying the stack also.
But there's only one kernel stack, right?
Okay, I see. So what basically, okay, so now you're asking how many kernel stacks there are. Right, so that's your question, good. So, okay, so there are two ways a kernel is implemented. One is the process model. Where there is a kernel stack, separate kernel stack, per process. Right? So in this case, what will you do on a fork? You will create a new kernel stack, and you will copy the entire kernel stack. So apart from the user address space, which has nothing to do with the kernel stack, right? And so you're going to have a separate process kernel stack per process. Right? So when you fork, you're going to actually have 2 stacks, and you're going to call iterate on each stack independently. So that's how you implement 1 entry and 2 exits. Right? There's another model in which you can implement things, which is called the interrupt model. So this is basically how you implement your kernel. In the interrupt model, there's just 1 kernel stack per CPU. So let's say there's just 1 CPU in your system, then there's just 1 kernel stack. And so now what the kernel needs to do is that it needs to store. So what will happen is that there's just 1 kernel stack, and that's the value that goes into SS0 and ESP0 that the hardware knows, and that's permanent. And so whenever you enter on that stack. But you are going to, when you switch, so let's say when I was, let's say a process made a fork system call, and I was executing on the stack, and now I created a new process called child, and now I wanted to switch to the child. So what I'll do is I'll save all the contents of the kernel stack in some other data structure, and load the contents of the child's stack from his data structure into this stack. Right? So eventually it's the same thing. You basically need separate states in the kernel, which simulates a stack per process. Right? In this case, you're actually having a separate kernel stack per process. In this case, you actually have only 1 stack which is visible to the hardware, but internally you are swapping state to basically fill that stack. Right? In this case, you will actually tell the hardware. So on each context switch, you're going to tell the hardware that this is the value of SS0 and ESP0 you should use. Right? On every context switch, you change the hardware structure. In this case, on every context switch, you don't change the hardware structure. You just do this internally. One of them, we only have 1 CPU, let's assume, okay, and then?
So we cannot call them parallelly, both the iterates, right?
Yeah, so you cannot, let's say there's just 1 CPU. So what will happen is one process made the fork call. It created a new process. It added it to the list of processes that are possible to run, right? And now let's say the parent continues to run. So parent is going to call iterate, and now parent can continue to run, and then let's say the parent says, I want to get out of the CPU, or let's say a timer interrupt occurred and the OS forcibly brings him out of the CPU, and now this process's turn comes, and so now he gets to run, and now he'll call iterate.
But at that point, we already popped out all the ESP.
No, we popped out things from the parent stack. So we have a separate stack per process, right? So we popped out things from the parent stack, the child stack still remains.
So in the interrupt model, what is exactly happening as in once you have popped from the parent stack?
In the interrupt model, it's basically the same thing, except, you're basically storing the value with which the stack needs to be initialized when it gets context switched.
And we are storing
In some data structure, right? So let's say in that process, in the list of processes, you're also saying, these are the values with which you should initialize the stack before you start it running. Okay? So there's no fundamental difference really. In one case, you are exposing it to the hardware. In the other case, you are keeping things internally. All right? Okay. All right, so yeah, question? Right, so what will happen, so this seems to be confusing people, that what happens in case of 1 kernel stack. So let's say there's just 1 kernel stack, all right, but each time you context switch, you are going to reinitialize that kernel stack with certain values, right? And so in case of a parent and a child, you store that, this is what you should initialize it before you start running it. Okay, so that's the difference.
But sir, then where is that stored? Where are these values that need to be stored actually kept?
In the clearly in the OS address space. So where are these values stored? Clearly in the OS address space. How they are stored? In some data structure, which is maintaining the set of all the processes and associated information. Right? In any case, when I have a separate kernel stack per process, I'm also storing the stack with the process, right? So this is your stack, this is my stack, this is his stack, etc. And so I'm going to load the ESP with that stack. In this case, the ESP remains the same. I just initialize the memory locations. That's the only difference. All right?
So is it possible that we can copy all this file content to some registers and then we can push it to the stack so we have twice the copy of the same?
Is it possible to make 2 copies of the same thing on the same stack?
Yes.
I mean, intentionally or unintentionally?
Intentionally.
Okay, and then why?
And then first time when we call iRed for either child or parent, then we get the first 5 values, and then second time when we call, we get second 5 values.
No, it has a lot of problems. So the question is, can we use the same stack for both the parent and the child, and actually have 2 frames, one for the child and one for the parent, and use the same stack and not having to context switch? There are also other processes in the system, right? So I mean, the cleaner way would be that you basically say that this is yours. This is how you should initialize things. So it's possible that between the parent gets to run and between the child gets to run, there are other processes that get to run in the middle. So why would you want to do that? Okay. All right. So your programming assignment, you are now roughly ready to actually start on your programming assignment, and you should start on it immediately. Okay. All right. Okay. So let's stop.